And now it is my pleasure to introduce Pete Smith from the University of Aberdeen, who's going to tell us all about how we can have negative emissions through soil management.
Thank you. Cheers. Yeah, so I'll talk about using soils for negative emissions. So mostly what I'm going to talk about today is summarised in a couple of papers. Well, one was published in Global Change Biology in 2016, and another published in Nature the same year. So of the different negative emissions technologies which we've looked at in the Global Carbon Project, we've got direct air capture, enhanced weathering, afforestation, reforestation, BECCS, and then we've got soil carbon sequestration and biochar, and it's just the latter two that I'll focus on today. But every now and then I will show some of these other technologies just for comparison. So it's just worth spending a couple of moments on explaining how soils are a negative emission technology by comparing it to some of the others. So if we look at the top left here, this is our business as usual fossil fuel energy. We're taking the carbon from out of geological storage. When we combust those fossil fuels, we put the CO2 into the atmosphere. That's why we're in the trouble that we're in at the moment. What we can do is we can capture that. So what we've just heard from Jen is, well, it's DAC, but it uses some form of carbon capture and storage, where we just burn the fossil fuel, we capture that carbon, and we return it to the geological reservoir. So that's not a negative emission technology. It's just preventing a flux of carbon to the atmosphere. With some of these other ones, if we just use bioenergy, again, this is not a negative emission technology. We're taking CO2 from the atmosphere and capturing it through photosynthesis, and then we're burning that biomass for energy, but that biomass is then going back into the atmosphere. So we're just cycling here. It's not carbon neutral, but we're just cycling the carbon between the land sink and the atmosphere. So this is business as usual. Neither of these are negative emission technologies, but from D onwards, these are all negative emission technologies in that there's a net removal of carbon dioxide from the atmosphere, either into geological storage or into the land pool or into the ocean. So with BECCS, we've heard a lot about that this week, where it's the same as bioenergy, but when we burn the biomass for energy, we're capturing those biological emissions and putting them down into geological storage. So there's a net transfer of carbon from the atmosphere into the geological storage. Direct air capture, which Jen's just talked about, is taking carbon from the atmosphere and putting it back into geological storage. Enhanced weathering is doing a similar thing by reacting minerals that naturally react with CO2 and putting that into geological storage. And then the others, which include soil carbon sequestration, are actually taking carbon from the atmosphere and storing them in shorter term pools with turnover of maybe decades, maybe even centuries in some cases, but with a range of turnover times, so that you've got a net increase in the land carbon sink. So soil carbon sequestration is one of these technologies which takes carbon from the atmosphere and puts it into the land, but not into geological storage. Biochar is quite similar in that we're doing a similar thing, and we're probably then using that biochar as a soil amendment. People who know a lot more about biochar in the audience than myself, but we're moving carbon from the atmosphere and storing it in the land. And the purpose of using biochar is that through that pyrolysis, you're making the material more recalcitrant. So you would hope that it would stay in this land pool for longer than just the normal unamended soil organic carbon. So these are the ones I'll focus on today: soil carbon sequestration and biochar. So we can look at the impact. So we don't only need to consider the impact on negative emissions. We can compare the potential, and I'll come on to those global potentials in a moment. But we need to consider the impact that it has on other ecosystem services and other things that we use. So in terms of the land, the land footprint, so these are all expressed on a ton of carbon equivalent. So just looking at when you remove a ton of carbon, what's the impact on nutrients, water, land, etc. So from the land perspective, soil carbon sequestration, you're maybe, to get per ton of carbon removed, you maybe need something like 20 to 30 hectares. With biochar, it's smaller because you can put on larger amounts and it sticks around for longer. But the important thing to note with soil carbon sequestration is that this is not occupying land. So when we do these calculations for afforestation or for bioenergy with carbon capture and storage, we're taking land out of its current use and we're putting it into another use. What's good about soil carbon sequestration, or biochar for that point, is that you can use exactly the same land and you don't have to change it. So you can increase the soil organic carbon stock in your agricultural land and you can still produce food from it. So even though it has a land footprint, it's not an exclusive use of that land. In fact, it can enhance production, which I'll come on to in a moment. So you need land to do it, but you don't need to take land out of its current use to do it. In terms of nutrients, this is something that's been raised recently, particularly in the context of the French government's 4 per mil initiative. They're saying we've got a fixed stoichiometric ratio between carbon and the other elements. So if we're trying to increase the carbon stock by, say, a gigaton, then we know that we're also going to increase the amount of nitrogen, phosphorus and potassium that we need because we have those sorts of fixed ratios. So you can either look at this as a positive thing, that we're maybe locking up some of these other nutrients. So if that's in soil carbon, we've got some of these available. If you look at it in a negative way, for every ton of carbon, then maybe you need 100 kilograms of nitrogen because of this stoichiometric ratio of about 10 to 1 between the nitrogen and the carbon. So one thing that we maybe need to do, if we're going to be growing the soil carbon stocks, we may need to have some form of additional fertilization of NPK. So you can see here that particularly in terms of nitrogen for soil carbon sequestration and for biochar it's more an issue of potassium, then we may need to be adding some of those external inputs to the soil. Albedo is also an impact because pyrrolized material tends to be darker. There can be significant impacts on the albedo. So you're presenting a darker surface. That darker surface is less good at reflecting the sunlight, so you're changing the albedo, and you can actually have a significant impact there, particularly if you've got a relatively light-coloured soil and you make it darker, then you're having some non-greenhouse gas, non-carbon biophysical climate impacts. So these are things that we need to take account of when we're considering darkening the soil using biochar. So it's something that we have to feature into the calculations. In terms of energy, it doesn't take any energy at all to increase soil organic carbon. These things are close to current practice. So it's things like changing your cropland management, agricultural management, deeper rooted plants, changing the tillage and residue practice. These are things that we know how to do, so they're quite close to common practice, and it doesn't require any additional energy to do that. With biochar, it's an exothermic reaction, and depending on how you do it, how the pyrolysis works, you can actually gain some energy, and energy may be a byproduct that you can sell in a similar way to bioenergy with carbon capture and storage. And then lastly, in terms of the cost, this is looking at the cost range. A lot of the soil carbon sequestration methods are very, very low cost or are cost negative. So we can do them at low cost, or sometimes we can even do them that we get a gain through increases in agricultural productivity and such like. With biochar, the range of estimates is much larger, and that's predicated on the market for the biochar. So if you can sell the biochar, you've got a viable market if you're selling it as a soil improver, for example, for horticulture, then you can get into cost negative. And if you've not got an adequate market, then you can end up with fairly high costs in some situations of producing that biochar. So these are some of the sort of environmental externalities or the limits associated with soil carbon and with biochar. And what we can do with these, and what we can do with all the other negative emission technologies, is we can aggregate those up to the global level in a very simple-minded way to see how they all fit out. So I'll just show you a graph which has this on. So I'm going to walk you through this one because it's absolutely horrible. What we've got on here, direct air capture, BECCS, afforestation, reforestation, enhanced weathering, biochar, and soil carbon sequestration. What's on, if this is the central line, this is zero energy. If you're on this side, over on my left, your right of the graph, you're looking at technologies that require energy. So as Jen has already said, with direct air capture, you've got quite a large energy cost. With bioenergy, with carbon capture and storage, you're generating energy. So it doesn't require energy, it actually produces energy. What's shown up here is the global potential, and this is set to 3.3 gigatons, which was the median from all of the integrated assessment models from the last IPCC assessment report. So what we've done is said, what would happen if we tried to implement technologies either to their maximum level or to that sort of level that you require for negative emissions? And you can see that BECCS and direct air capture give you a potential of getting to that round about 3.3 gigatons. If we're looking at biochar and soil carbon sequestration, we're down here at less than a gigaton of carbon, but that's still, you know, maybe sort of 3 or so gigatons CO2 per year, so not negligible. The other things that the graph shows is the bigger the blob, the higher the cost. So the relative cost here, direct air capture is at the moment very expensive. Relatively low cost associated with soil carbon sequestration and biochar. The other thing that's shown is the colour. The colour of the blob gives you the land requirement or the land footprint at the global level. So if you've got green colours, then there's a relatively small land footprint. And as you go through these warmer colours into the purples, for example, wide deployment of afforestation, reforestation or BECCS, you've got quite a large land footprint. And the only intuitive thing on the whole graph are the water droplets. The water droplets give you the water footprint. So the more full those water droplets, then the higher the water footprint. So what we can immediately see from all of these negative emission technologies is there's not one that jumps out in the perfect space. You either have a high energy cost, a high land footprint, a high water footprint, or you've got a relatively limited potential in terms of greenhouse gas removal or negative emissions. So that's why it's coming up again and again that we, at the moment, when all the horses are lined up at the start of the race, there's not one that we can back. There's not one that we can say, this is the one that we're going to put all of our money on, because we don't know how this is going to pan out. And we probably need a spread bet, a portfolio of measures, which are applied in the most appropriate places to do this. But the ones I'm going to focus on a little bit more are the biochar and carbon sequestration, because we've got about somewhere between about 0.5 and a gigaton of carbon negative emission potential, but a low water footprint, a low cost, and a low land footprint. So these might be regarded as relatively low cost, but relatively no regrets options that we could do in a widespread way that would have limited externalities associated with the environment and in terms of costs. So some other estimates were made in this, the Keith Poustian's Nature paper, and this is just showing you the sort of the negative, the greenhouse gas removal potential per year versus the area that you need to practice it on. So you can see here that there are some practices for soil carbon sequestration and for biochar, which require large land areas but have relatively low potentials. Or there are some options over here for restoring histosols, the peatlands, which have much smaller areas but give you much more bang per unit area. So a combination of these practices through set-aside, restoration of degraded land, rice management, these enhanced root phenotypes to get more carbon down into the soil, and then all the things we already know about in cropland and grazing land management, as well as restoring these peatlands, give us a quite significant potential. And this has come up again. It's attractive to policymakers because it gets around some of the issues associated with the negative externalities about some of the technologies that require large land areas and may either displace food production or may impact upon biodiversity. So this was another paper that came out last year by Bronson Griscom and colleagues looking at natural carbon sequestration or natural climate solutions. So this has been quite popular with both NGOs and governments because there's probably going to be higher public acceptability for many of these options. So afforestation, reforestation, a lot of it to do with restoring degraded forests and restoring coastal wetlands and peatlands. Now, these are things that are being pushed on the biodiversity agenda, but they also give us quite significant negative emissions potentials. So some of these, and again, this includes both vegetation and soil, particularly with the peatland restoration. We're looking at soil pools. And then we've got these agricultural and grassland measures, which add up to something significant if we apply them over large areas. So you will have seen also this graph that Sabina has shown a couple of times. This is just looking at where soil carbon sequestration and biochar fit in this whole portfolio of measures. You probably won't be able to see everything from the back, but G is soil carbon sequestration. And you can see here that it's got a negative removal potential. This is from a big systematic meta-analysis of the literature. It's got a large potential here at relatively low cost, in fact, going down to cost negative. So it occupies a space on this negative emissions sort of parameter space, which is low cost and actually gives us quite a large potential. And if we look at biochar, biochar is C. That's on here, also relatively low cost, maybe slightly smaller potential at the global level, according to all of the literature that's currently out there. And then if we look at some of I'm going to be coming on to this at a moment, so the issue to do with soil carbon sequestration is the permanence, so I'll come on to that in a moment. There's also the saturation issue, a similar one but less so with biochar. And then we've got these side effects. We've got some positive side effects. For example, biochar reduces nitrous oxide emissions, so that's good for the climate. Soil carbon sequestration is able to enhance productivity. So we've got some co-benefits. So those co-benefits require a little bit, just a slightly more time, just a slightly bigger examination of those. We've got all these sustainable development goals which we want to meet. And Saskia Keister and colleagues put together this way of conceptualizing where soils fit into this sustainable development goals issue. So we decided we're going to write a review paper looking at soils and the sustainable development goals. And when we first started doing it, it was very scattergun. So he sort of said, oh yeah, it's going to be good for food security, it's probably going to be good for climate, and we had no way of organizing all of this information. But Saskia came up with this idea of putting the soil carbon sequestration in the middle, looking at the soil functions that are provided by the soil and how they relate to the Sustainable Development Goals, how those soil functions underpin the ecosystem services, and how those ecosystem services underpin the Sustainable Development Goals. And that gives us a way of going from soil carbon sequestration in the middle out to each one of these Sustainable Development Goals, which are shown in the outside ring. And wherever you see a red dot, this is where there's a soil function that's underpinning the Sustainable Development Goal. And whenever you see these sort of green blobs, that's showing where an ecosystem service is supported by the soil that's helping to deliver to those Sustainable Development Goals. So what I can hope you can see here is that soils are contributing to a really wide range of these Sustainable Development Goals, some of them really, really significantly. So we've got a whole bunch of co-benefits. So what's good for the policymaker is that even if you've got no carbon sequestration, no greenhouse gas removal, we've made the world a better place anyway. So it's a no regrets option. It's got a whole bunch of co-benefits, and that's similar for some of the others. So if this is so fantastic, why aren't we doing it? Well, we are, but this is some of the caveats. So this is some of the things, some of the relative issues associated with soil carbon sequestration. The first one is saturation. the second one is permanence, and the third one is leakage and displacement. So I'll just say a little bit about each one of those. So the first one is that they saturate. So if you've got a direct air capture machine, you can keep it running, and as long as it's running, it's removing carbon dioxide from the atmosphere. And if it is maintained properly, that would continue removing carbon dioxide from the atmosphere. The issue with soil carbon sequestration is that it saturates. So when we do a management change here, we've got degraded soils, we do a management change, then after, say, a period of 10 years, we've had a quite significant greenhouse gas removal or negative emission. The next 10 years, we get a bit less. The next 10 years, we get even less. So after about 20 to 50 years, we're having to maintain this management, but we're getting no net removal from the atmosphere. So we're locked into a situation where we're having to maintain the management, even though we're no longer getting any net removal from the atmosphere. It's similar with any biospheric sink. You would get a very similar shape if you think about these are trees growing, for example, and they're reaching maturity. So the sinks saturate. So after 20 to 50 years, we're having to maintain those management practices, which are probably good anyway. They're good things to do, but we're getting no net removal. The other issue is the reversibility. So it takes us a long while to increase soil carbon, but if we mess up our management practice, if we go back to bad practices, we can very, very quickly lose that. So it's much easier to lose in biological processes everything I've found apart from losing weight. That's the only situation where it goes totally the opposite direction. Good, yeah, some other fat is in the audience, thank you. But it's a process whereby you can really easily lose that quickly. And the last issue is that we've got this leakage displacement issue. So you sort of say, here's my piece of land and I've increased the soil carbon, so give me a carbon credit. The problem is that if you're taking, for example, if you've got manure applied here, you've got manure and mineral N applied there. If you move your manure from this here over to that there, and you only report the soil carbon increase here, you're actually decreasing the soil carbon there. So the net landscape change is zero. So we need to make sure when we account for this that we're taking a full landscape scale approach. So there are significant issues in terms of saturation, permanence, and these additionality issues which we need to consider. But in many other respects, I think soil carbon sequestration and biochar are relatively sort of no-regret strategies. So I think there's moderate negative emissions potential. So we're talking, maybe 0.5 to 1 gigaton of carbon per year globally. So maybe 3 or 4, maybe up to 5 gigatons CO2 per year from soil carbon sequestration and from biochar. They can be deployed immediately and at scale. Farmers know how to do this. Land managers know how to do it. Biochar, I'd say, requires a bit more research to look at some of the externalities, how it can be combined, for example, with enhanced weathering. What are the interactive effects? If we're going to be putting on silicate, rock dust, and biochar together, we don't know what the interactions might be. Saturation and reversibility are the main drawbacks. So that's the thing that scares away some policymakers for putting these practices in place because they think this is not going to be a permanent sink. There's a number of co-benefits associated with soil carbon sequestration, and I think also some for biochar, but maybe we need a little bit more on R&D to understand those better. But I'd say, given that big diagram showing how we've got a large co-delivery towards all of those sustainable development goals, we've got enough information to move forward and to start to do those things. When we put it in the context of all the other nets, they've all got limits and downsides. So the fact that we've got saturation and permanence issues associated with nets, then we've got energy costs and we've got economic costs and such like with the other nets. So because none of them are perfect, this should be, I think, part of the portfolio. And we need more large-scale demonstration projects as well as R&D. So let's try and do this and see how it works, because we learn when we do. And then I've just got this generic thing up because sometimes I'm talking to policymakers. I know everybody in the audience gets it, but people sometimes miss it and think that nets is an excuse to not mitigate. So I know you know that, but I'm just putting it out there just so that everybody else knows that we have to immediately and aggressively reduce greenhouse gas emissions. And then we do these things on the top. It's not a replacement for what we do it. And I think it's probably going to be really, really difficult, as we've heard with some of the excellent talks yesterday, to meet the Paris targets without negative emissions technologies. So we probably need to do both. I'll leave it there.